I'll do a quick introduction here. I know many of you, but I know we have a lot of new faces that I hope to meet and greet someday here soon. I'm a senior environmental scientist with Tetra Tech, and I've been working on the Middle Rio Grande throughout the West and Southwest for the past 20 plus years with many of you, and I know a lot of us are saying 20 plus years, so that's the term I'm sticking with from here on out. Doing a lot of restoration work, restoration on the river in and around Albuquerque, all the associated, compliance that goes along with that. Previous to Tetra Tech, I was with the Corps of Engineers for almost 14 years, and City of Albuquerque Open Space prior to that. So I've been doing a lot of work related to the species and the collaborative program. Joe joined Tetra Tech about 3 years ago, and he's done a lot of work throughout the West and Southwest on wetland delineation, permitting, also wetland restoration, upland restoration. He's a great botanist in terms of habitat sampling and mapping. And then especially the remote sensing that Chris talked about, LiDAR, GIS modeling, and he's going to be talking about that in some of the results for this study. So I just wanted to give a little bit of background to this. There was actually a first part to this study that was published in 2015. We worked on from 2013 to 2015. When I was with the Corps of Engineers, I was the project manager, and we had Tetra Tech do the work for the collaborative program. And at that point in time, as Chris had mentioned, we were starting to see a lot more Tamarisk leaf beetle activity, and that impacting Southwestern Willow Flycatcher habitat, and what could we as the program do in terms of trying to get ahead in terms of restoration planning. So pulled together, Tetra Tech at that time pulled together all the information on what we had in terms of plant information, Hinkenomart, territory data, fire, saltcedar, Tamarisk leaf beetle, and other stressors. And initially in that 2015 report, identified 25 areas with 103 potential sites. So if you look at the map here to the right, that's an area, and then there's a number of sites, and their different colors are different priority levels. At that time, the study went from Los Lunas down to the Elephant Butte Reservoir. So in 2018-19, the Corps and the program asked us to then update that study, both knowing we had further effects of Tamarisk leaf beetle, which I'll show you some graphics here in a minute, but also evaluating the changes since the original study, trying to look a little more at the metapopulation connection. So we had a lot of territories, smaller territories in different areas. We didn't have them before. How could we connect them more so that the birds could move throughout the system? And then again, still trying to get ahead in terms of restoration that could be done prior to additional Tamarisk leaf beetle impacts. So the current study contained all of these components. I'll just show you real quick and I'll come back to that. So Tamarisk leaf beetle through 2018, as you can see here, we knew we were going to be getting to the point where it was converging from north and south in the Middle Rio Grande into the Albuquerque Socorro area, so that by 2019 you can see the straight line through there. So in that effect, Tamarisk leaf beetle is basically throughout the Middle Rio Grande. So it was sort of a considered, we didn't have to necessarily map it, we knew it was there everywhere. Also, the current study updated the vegetation. Originally, we used the 2012 Hinkenomart mapping. We updated to the 2016 Hinkenomart mapping. And then we also looked specifically at these sort of A and B groups. What are sites that have currently greater than 25% saltcedar, but also sites that have less than 25% saltcedar? Maybe they would be a little easier to do some restoration work on. Also updated the groundwater model, had since the previous model more data that could be included there to make it a little stronger. Also looked more specifically and coordinated with Fish and Wildlife Service on, let's look at the territories and trying to get that distance between 10 miles is the number we were getting so that they could have places to go in between. And then also looking at areas where they did not want restoration to occur because the birds were doing well there. And then also some particular areas they wanted us to look at. Also, since that time, a lot more completed habitat restoration projects and unfortunately fires. And then within all that, there were some anomalies. So we did look at a couple other different things just to verify. We looked at the habitat suitability model, which also used the 2016 Hinkenomart data. Also the USGS habitat model, which was further verification when looking at sites to verify what was going on there. Some normalized difference vegetation index verification. And throughout all that, also came up with some alternative sites. So now Joe is going to talk about the results.
Great, thank you, Ondrea. That was a great overview for the project. I'm going to take the remainder of our presentation time walking through the process that we went through to develop the flycatcher Tamarisk leaf beetle habitat restoration siting model. So we started the project with a deep dive into the flycatcher nesting habitat literature and spatial data sets available for the Middle Rio Grande. Once that was completed, we set up several meetings with the collaborative joint work groups, which included subject matter experts, researchers, practitioners, regulators, and land managers. Frankly, most of the participants in those meetings wore most of those hats. But during those meetings, we presented our current findings and communicated the direction that we were taking the study, and then we facilitated an open forum to discuss the opportunities and constraints, and to pretty much make sure everybody was moving in the same direction, and we all agreed on what direction that was, which can be challenging, but it was they were all very productive meetings. One of the more obvious benefits that resulted from the early collaboration was a clear definition of our area of interest. I was honed down to between Los Lunas and the full pool extent of Elephant Butte Reservoir. So aside from just getting the final study area finalized, that was really just the tip of the iceberg in terms of the value that the meetings yielded. It's hard to overstate the value of getting a bunch of smart people in a room and talking about and linking their respective specialties towards a common goal. So big thanks to everybody in the program that helped us and helped us make those meetings successful. Let's go to the next slide. Once the study area was defined, we moved into the beginning stages of the site selection process. Now, the Hinken-Omar community structure vegetation mapping was an extremely powerful tool for the project, and we used it as the primary classifier for the analysis. Once that was, I guess, established, we then looked at what we were considering hard constraints, which included things like a patch size. We wanted a patch to be greater than 5 acres and or be expandable or link into adjacent habitat to have it a minimum 5-acre patch size. The next hard filter was a depth of water. And so once, because obviously the habitat creation for flycatcher is going to require depth of water that is suitable for the coyote willow and tree willow to become established and persist. So once we got those hard filters in place in the model, we ended up with approximately 200 potential restoration sites within the study area. We enumerated those sites and then began looking at the secondary filters, such as ease of transition from unsuitable to suitable habitat. Again, going back to the Hinken-Omar community structure mapping within the project area. And we looked at ecological site potential, which we interpreted via the normalized difference vegetation indexing, and using multiple years of aerial imagery. We also looked at the inundation mapping. LiDAR data were available, and a long list of other spatial data sets. This review allowed us to identify 50 sites with the highest restoration potential for the flycatcher. Once we had our 50 semi-final sites, we initiated field activities to field validate the sites. Field validation included depth of water evaluation, soils, indicators of inundation, vegetation type validation, vegetation density, as well as access. I think access and land ownership are two really important components of our restoration project, because we wanted to make sure we're providing practical sites, and that includes sites that added value, which includes easy access and constructability. We can go to the next slide. So through the field validation, we honed the 50 semifinal sites to 9 final high priority sites. The sites represent the low-hanging fruit in terms of flycatcher restoration. It's based on some, I guess, value items such as ease of access, cost effectiveness, metapopulation, habitat resiliency value. It's kind of a mouthful, and as well as ownership, as I mentioned before. Now, just because we came up with a list of the 9 final sites doesn't mean that the 50 semi-final sites don't offer value. So we made sure to memorialize a master habitat restoration siting matrix for all 50 sites within the studies report. Let's go to the next slide. Okay, so this is site 1, also known as A43, based on the original enumeration for the sites within the project. And this is the type of information that we compiled and present in the final flycatcher report, or flycatcher habitat restoration siting report. I think we are a little bit short on time, so I'll just go through some of the, I guess, the outline of it. So we're looking at the site size, post-restoration habitat patch size. It was a really big one, so we want to create large habitat patches that allow for large populations. And we also get into the vegetation, habitat, hydrology, disturbance history. Yellow-billed cuckoo is something I want to make sure we bring that up, because that was a complicated hurdle to overcome for the project, and we had to eliminate several sites because they were nearby yellow-billed cuckoo habitat or corresponded to yellow-billed cuckoo habitat, and bad practice to take habitat from one endangered species to create habitat for another one. All right, we could probably go to the next slide. Okay, so then we get into the lessons learned, and this was a challenge. How do you come up with a lessons learned slide for a study that took 2 years and consumed a lot of your bandwidth for those 2 years? But at the end of the day, I guess some of the high level lessons learned on this project and some of the value that we were able to glean from the project was just a full spatial data inventory for the Middle Rio Grande. We looked at every single piece of data that we could get our hands on and compared it to a flycatcher nesting, both present and past, to see which ones correlated to flycatcher nestings, and then also basically looked at the value of each one of those data sets in terms of precision and accuracy, and just went through our own filtering process for all of the data sets within the Middle Rio Grande. And so some of the really big ticket items in terms of the value presented to the project included the inundation mapping. I can't say enough about this. Everybody knows about it. I think probably more so than any other data set, the mapped inundation from previous floods in the Middle Rio Grande corresponded to flycatcher nesting more than anything else. Also looking at the streamflow modeling, which allowed us to look at the potential for inundation in any given year along the entire Rio Grande or Middle Rio Grande. NDVI was priceless. Vegetation density with LiDAR was, especially when paired with NDVI, where we get vegetation height and density and productivity. I mean, that was a very powerful tool when we're looking at the probability of flycatchers utilizing an area, or even in this case, evaluating site potential. Because it stands to reason that sites that have very high density of mixed Tamarisk, saltcedar, and native species is going to support high density native species, which obviously the flycatcher require. And then vegetation type and patch size, again, with the going back to the Hank and Olmart, that's been a long-standing data set that's been continually improved, and in terms of the amount and type of information that's available and the accuracy of the mapping itself. And so that was, again, that was the foundation of this project. And so I guess I'll just close with the models and modules, and that's just the correlations that we found between these data sets that were incorporated into our model. I think that's a very important component, just understanding the power of the data sets. And then also because, we have a model, but the model is really comprised of a series of modules. And a module is something that you can pull out and plug into the model based on project needs. And so that means that our flycatcher saltcedar habitat restoration siting model is very easily adapted to pretty much any other habitat restoration or just straight up restoration siting. For the Middle Rio Grande, all we have to do is pull out certain modules and plug in other modules to get the results or to meet the goals that we need for any restoration siting circumstance in the Middle Rio Grande.